this video, I want to do an example problem solving Newton's second laws and kind of showing or demonstrating the use of free body diagrams and kinematic diagrams. So in the problem here, I have a 200-pound box sitting on the floor, and I'm going to push this box by applying a force. Now the box is kind of low, so when I push on it with my hands, I'm kind of angled downward and I'm leaning on it to push it forward. So that force ends up getting applied at a 30-degree angle as shown in the picture. And what I want to find is how hard or how much force I have to apply to this thing in order to get it to accelerate at 10 feet per second squared. One other thing that I've specified here is that I have a kinetic coefficient of friction between the box and the floor of 0.25, so that'll become relevant for us. So the first step that we probably want to do, as is usual in many problems that we would do in dynamics, is create our free body diagram. So I'm going to go ahead and take and redraw my box by itself. And because I've taken this box and I've separated it from any other interactions or anything else, I need to make sure that those interactions are represented. So I've removed the box from the floor, which means I need to replace that interaction of the floor with a normal force acting on the box. I've still got my externally applied load, P. However, I'm going to go ahead and separate that force into two components, Px and Py. So those are going to be just Cartesian components of the force P, such that I can break it apart into those x and y components. I also have the weight of the box acting at its center of gravity, presumably right in the middle. We don't have any geometry for the box, so we're going to have to assume that it's symmetric and that everything is happening there right in the middle. And then the last bit, because again that I've removed this box from the floor and I'm pushing it causing motion, we're going to have friction, right? And friction always opposes our direction of motion. Since we're pushing it to the right, my friction force has to be to the left. And I think I've got everything included now on my free body diagram. I'm going to set this free body diagram equal to a kinematic diagram. So our kinematic diagram could include, in a planar case, in a planar problem, three separate things. It could include rotation, it can include translation in the x direction or translation in the y direction. Now for this problem, I'm going to make a couple of assumptions. One is that the box is being supported by the floor and therefore it's not going to move up and down. I think that's pretty reasonable. Also, I'm going to make the assumption that I'm not going to be pushing hard enough on it that it's going to rotate. Now we could actually solve that problem. We could include that rotation and see if the friction would actually cause us to push the box over. However, I think we can use lived experience to say that probably that's not going to happen. So I'm going to neglect any rotation, which means that the only thing left on my kinematic diagram is the fact that this box is going to accelerate to the right hand side, or in a right hand direction. So with these diagrams, I can start writing my equations of motion. So I'm going to sum my forces in the x. I have a px in the positive direction. I have a force of friction acting in the opposite direction. And I have a mass and my desired acceleration of 10 feet per second squared. Now, mass I don't actually have yet, right? However, we know that weight is equal to mass times gravity, and therefore I can solve for mass given that I've specified that it weighs 200 pounds. by dividing by gravity. Now I should probably clarify there, the 200 pounds I'm going to assume is a weight in pounds force. Of course, there is this thing known as pounds mass, which is kind of a goofy unit that sometimes gets used in textbook problems and such. However, I think in any sort of real application, if somebody says something is 200 pounds, you're going to assume that it's a weight and not a mass, and that it's measured with respect to Earth gravity and so forth. So I can go ahead and take my 200 pounds, divide it by my 32.17 or 32.2, depending on how accurate you want to get. Everything in engineering is an approximation anyways. And I'm going to get 6.2 slugs, or nice fancy unit of mass. Noting, again, that a slug is a pound foot per second squared. Kind of an ugly unit. All right, so with that, I can take that 6.2 and I would sub that in over here. Okay, now I can sum my forces in the y direction. In the y, I have a Py acting downward. I have a 200-pound weight acting downward, and I have a normal force. And if I'm suggesting that there's not going to be any vertical motion, then I can set that equal to 0, right? Because my kinematic diagram doesn't have anything over there. Now, what you might notice if we look at this is that we have 1, 2, 3, 4 unknowns potentially that could be problematic, right? However, we could potentially throw in a third equation. We could do a summation of moments, but I already said that we're neglecting rotation and anything there, so that's probably not going to help us too much. One other thing that we can remember, though, is that force of friction is equal to friction coefficient times normal force. So that, given that we know what mu is, allows us to make that substitution and kind of eliminate a variable there. Now the other variable that I can eliminate is that px and py are not actually two separate variables, right? Because there's only one force p, and px and py are related to that via trigonometry. So in reality, we only have p and n as our variables. We have two equations, two unknowns. Everything looks to be satisfied. Okay, so I'm going to take that then and start rewriting our equations with some of these things that we've now specified. So first, starting with the summation of forces in the x, px is p cosine 30 minus 0.25 n equals 62. And in the y direction, I have minus p sine 30 minus 200 plus n equals 0. So again, two equations, two unknowns. Probably the easiest way is just to brute force it. So I'm going to go ahead and solve for n in this second equation by adding p sine 30 and 200 over to the right-hand side. And I'm going to take this solution for n and plug it in to my forces in the x direction equation. Doing that, I get p cosine 30 minus 0.25 times p sine 30 plus 200 equal to 62. I'm going to pull my variable p out of both of those equations. And I've got something now that I can rearrange and solve for p, which is 62 plus 50 over cos 30 minus 0.25 sine 30. Oops. And this I can plug in into my calculator, and I can solve that out. And I can get an answer of 151.4 pounds as the load P that I would have to apply to this box at that angle in order to get it to accelerate to the right at 10 feet per second squared. Probably reasonable. You know, a little bit difficult, but I think probably within the realm of something someone could handle. All right, thank you.